This is called measurements in chemistry. So a few things, excuse me, a few things to get through here before we move into some of the measurements in chemistry. I want to mention to you something called physical quantities. Physical quantities require both a number and a unit. For example, 15 grams, 34.3 meters. You have to have a unit for it to make sense. So whatever it is you're talking about, height, volume, mass, temperature, you can't just have the number there. In the example, you can't just have 34.3. It's meaningless. You have to have a unit behind it. In this example, 34.3 meters. A number alone would mean nothing. So any physical quantity can be measured in many different units. For example, I can measure a person's height in meters, in centimeters, in inches, in feet, etc., right? So any physical quantity can be measured in many different units. So to avoid confusion, scientists have agreed upon a set system of units that we all use globally. That way we can compare our lab results to each other. We can compare, like you don't want to do one set of lab results in one unit and then have everything else come out in yet a different unit. You want your stuff to match up so you can compare with other labs around the world. So we have something called SI units to take care of that. SI really is just International System of Units. The reason why it's SI is it was French, Système International, as opposed to in the United States or in English, International System. So SI units is just the International System of Units. And here they are. Mass, kilogram. Length, we use the meter. Volume, we use the cubic meter. Temperature, we use something called kelvins. And then time is seconds. So look at that. Mass, kilogram, length, meters. See all volume, cubic, meters. Those first three look like giant units, something you might not want in chemistry. We'll get to that. Now, as a side note over here, I'm writing down some notes on what are known as the metric system. The metric system is not the same as the SI units, but metric system are also heavily used, especially in chemistry. So for mass, we use grams, volume, liters. Temperature, we like to use Celsius. So please note the difference between those two. Now, as I mentioned, some of the units up there are huge, way out of range for something so tiny, tiny, tiny as like the diameter of an atom, right? So metric and SI units can be modified by prefixes to refer to smaller and then even larger quantities. Example, diameter of a red blood cell would be 0.0000006. I think I said too many zeros, but you get the idea. 0.00006 meters, or we could just say it's 6 micrometers. That little curvy U is a micro. Example, distance from Earth to the Sun, 150 gigameters, or 150 and then 9 zeros meters. So you can see that prefixes come in very handy for putting our units into proper physical quantity amounts. All right, the next little snippet or little segment of notes for today is measuring length and volume. All right, well, length, if you remember from our last video, the meter is the SI unit, but this is too big in chemistry. Now, I did mention in video number 1 that we talk about something like called prefixes, and if the meter is too large of a unit, we can use things like centimeter or millimeter. All right, so the conversion factors for these guys are 1 meter is equal to 100 centimeters is equal to 1,000 millimeters. Now, volume down below here is the amount of space occupied by an object. Now, the SI unit is way too large. It's meters cubed. That's like a meter times a meter. I mean, I can almost fit in a meter cubed box. Okay, so it's way too large. So instead of using meters cubed for volume, the SI unit, instead we use these are metric units, and they're much more usable for us because the size is much smaller. So number 1 is the liter, capital L. We also use the milliliter, ml, and the cubic centimeter, which is centimeters cubed. The conversion factors for those three guys are 1 liter is equal to 1,000 milliliters is equal to 1,000 centimeters cubed. All right, so and we'll use more of that later on, and a lot of your homework problems will address some of that stuff. All right, the next bit of notes I want to talk about is the idea of measurement and something called significant figures. All right, so first some background information. Every experimental measurement has some degree of uncertainty to it because there's a limit to the number of digits that can be recorded. So let me read that again at kind of full speed. Every experimental measurement has some degree of uncertainty to it because there's a limit to the number of digits that can be recorded. Anytime you're measuring something, at the end, it's going to come down to kind of what your interpretation of that measurement is. So there's always going to be some sort of uncertainty. So the bullet point here says, so to indicate the precision of a measurement, the value recorded should be all the known digits plus one additional best guess digit. Now I'm going to elaborate on what I mean by this in just a second with some examples. But the value recorded should be all the known digits plus one additional best guess digit. And whatever that comes out to be, that is the number of significant figures in the calculation or in the measurement. All right, so what the heck does all that mean? Well, let's take a look at, I believe this is page 3 of our notes. Here's an example. And we have basically in between, it says which ruler is more precise. And in between these two rulers, we have, I don't know, a pin or a nail. I guess I'm calling it a nail here, okay? Well, our measurement, what we record and what we write down as our measurement in inches, depends on which ruler we're using. Now, the top ruler just gives me 1, 2, and 3, and that's it. The bottom ruler gives me 1, 2, and 3, but it also gives me 0.1, 0.2, 0.3, etc. So the bottom ruler is going to be a much more precise way of measuring this. For example, in the top ruler, I know for a fact, it is known that it's in between 1 and 2 inches. So I say 1 point, and then my best guess was 7. So 1.7 inches. How many digits are there? 1.7, 2 digits, okay? So the bottom one, I know for a fact it's in between 1.7, that bottom ruler, I know for a fact, if you really look closely, I know for a fact it's in between 1.7 and 1.8. Those are little tick marks. There's a 1.7 tick mark and there's a 1.8 tick mark. It's known. And I'm in between them. I got really close with my eyes and my best guess was a 4. So 1.74, 3 digits, 3 significant figures. 1.7 is only 2 significant figures. Let's try another one. Read the volume of the graduated cylinder to the proper number of significant figures. All right, so I've got some, looks like it's a colored liquid. That little curvature thing is the meniscus, okay? And it looks like I'm reading, you always want to read at the bottom of the meniscus. All right, well, I know for a fact I'm in between 16 and 17 milliliters here because there's tick marks, 16 and a 17 tick mark. My best guess, well, I came up with 0.2. I feel like it's closer to the 16 mark than it is to 17. So I say 16, and then my best guess, 0.2. 16.2 milliliters, 3 digits there, so 3 significant figures. All right, the little squiggly line at the top of the page means I'm moving on to something a little bit different, but not super different. So, determining the number of significant figures, sig figs means significant figures. Determining the number of sig figs is difficult when you have zeros involved. And I mean like the number 0. Some zeros we count, some we don't. So here are the rules, and I believe there are 5 of them. Yeah, there are 5 rules. So, first rule, all non-zero numbers are counted as significant. We've seen that actually 3 times on the previous page, I believe. So, for example, 457 centimeters, That's clearly 3 significant figures. So number 1 is a rule that is fairly straightforward and it's common sense. Number 2, leading zeros are never significant. Leading zeros are zeros that come before the non-zero numbers in a number such as this that has a decimal. Okay, so 0.0068, the 0 and the 0, those are leading zeros. They're never significant. We only have 2 sig figs. By the way, the 0 to the left of the decimal isn't even really there. If you were to take it away, it doesn't matter. Number 3, inclusive zeros are always counted as significant. These are also called captive zeros. These are zeros that are kind of stuffed between non-zero numbers. So 6,804 milliliters, 4 sig figs. That's an inclusive zero tucked in between 8 and 4. Next example, 0.06903 ounces. This is going to be 4 significant figures. We have an inclusive zero that counts, and then we have the leading zero that does not count. Rule number 4, top of the next page, trailing zeros. Trailing zeros, so in rule number 2, I said leading zeros are never significant. In rule number 3, I said inclusive zeros are always significant. Rule number 4, it depends. So for trailing zeros, rule number 4, it says trailing zeros are only significant if the measurement contains a decimal point. So for example, 913.0 kilograms, 4 significant figures. Trailing 0, which means at the end of the number, with a decimal. 9,130 meters, in the next example, 9130 meters, that's a trailing 0, but there's no decimal point. 3 sig figs. Next example, example number 3, 0.000700050 liters. 5 significant figures. You don't count the 3 leading zeros, not 4 leading zeros, remember. 3 leading zeros, they do not count. The 2 inclusive zeros do count, and yes, the trailing 0 counts because we have a decimal point. 5 significant figures, all right? All right, the last rule is regarding exact numbers. Now, these are not measurements. See, when you measure something, there's a certain degree of uncertainty involved because we always have a best guess at the end. So these are precision measurements. Exact numbers are counting numbers. For example, if I'm holding 2 marbles in my hand, there are exactly 2 marbles. It's not 1 sig fig because I have a 2 for 2 marbles. It's an infinite number of significant figures because there is no uncertainty. So exact numbers, these are not measurements, but they're counted. Example, 27 apples, infinite sig figs. 27 kilograms, 2 sig figs. All right? So if you have a dozen eggs, 12 is not 2 significant figures, it's infinite. A little sideways 8 for infinity. So let's do some examples. How many significant figures are in the following measurements? 3.45 meters, B 0.1400 kilograms, C 10.003 liters, and D 35 cents. Well, A is 3 sig figs, B 4 sig figs because we have trailing zeros in a decimal, C 10.003 liters, those are all inclusive zeros, 5 sig figs, 35 cents, you can actually count the pennies or the nickels and dimes, whatever it adds up to. Infinite number of sig figs. D, 35 cents, is a counted number, not a measurement. Some others. 2730.78, 6 sig figs. 0.0076, 2 sig figs. 3,400 kilograms, 2 sig figs. Trailing 0 with trailing zeros in 3,400 kilograms, but no decimal point. 3,400.0 meters squared, 5 sig figs. Trailing zeros in a decimal, they count. All right, moving on. Double lines means I'm moving on to a different topic. Scientific notation. Example. Convert the measurements from standard notation. Standard notation is just like a regular number. Convert the measurements from standard notation into scientific notation. So 58 grams, 5.8 times 10 to the first grams. 46.792 meters, 4.6792 times 10 to the 1 meters. 0.006720 centimeters becomes 6.720 times 10 to the minus 4th centimeters. That base number has to always be between 1 and just under 10. Okay. D, 345.3 kilograms. This is 3.453 times 10 to the second kilograms. All right, the number of significant figures I start with is the number of significant figures I end up with. Next example. We'll do the other way now. I'm going to give you a bunch of guys in scientific notation, and you want to convert the following into standard notation or just regular numbers. So 4.885 times 10 to the 4th milligrams, 8.3 times 10 to the minus 6 meters, and then the last one there. So let's top 4.885 times 10 to the 4th milligrams. Well, just move the decimal over 4 places to the right because of the positive 4, 10 to the 4th. 48850 milligrams. Okay, 4 sig figs, 4 sig figs. B, 8.3 times 10 to the minus 6 meters. We have 0.000083 meters. 2 sig figs for both. C, 4.00 times 10 to the minus 2 liters. That has 3 sig figs, doesn't it? So my answer will have 3 sig figs, 0.0400 liters. Now, in 0.0400 liters, we have a leading 0, doesn't count. The 0 to the left of the decimal is nothing. And then the 2 trailing zeros, they do count. So 0.0400 liters is 3 sig figs. All right, next topic, calculations and rounding with significant figures. All right, we got 2 rules here, very similar rules. The first rule is for multiplication and division. Rule number 1, and we use this rule the most. Rule number 1, when multiplying or dividing, the answer can't have more significant figures than either of the original measurements. So for the example, 278 divided by 11.70, well, the numerator had 3 sig figs, so that's why the answer was reported in 3 sig figs. All right, rule number 2. When adding or subtracting, the reason why rule number 1 is not more popular but used more often is because we multiply and divide more often in chemistry. Rule number 2 is for addition and subtraction. Rule number 2, when adding or subtracting, the answer can't have more digits after the decimal point than either of the original numbers that you're adding or subtracting. So basically, as far right as you can where both of them go to the right of the decimal. That was a little bit wordy. Let's just learn by example. We got 3.18 liters plus 0.01315 liters. Well, the furthest right that they both go is to the tenths to the hundredths place. So I draw my dashed line. My answer can't go any further than that. The rule is totally different than the multiplication and division rule. So I add these guys together on the calculator, and then I round it to the appropriate number of significant figures, 3.19 liters. Seems kind of funny that you have to drop some numbers on the calculator, but we do. 3.19 liters, 3 sig figs. Example, round, so now we're talking about rounding. Round to the proper number of sig figs. 2.304 grams, 188.3784 milliliters. C, 0.00887 liters. And then in parentheses, they tell us how many sig figs we're going to round these to. D, 1.00039 kilograms. 3 sig figs will be 2.30 grams. Don't forget the units. 5 is 188.38. We bump it up to an 8, rounding. C, 0.009 liters. D, 1.000 kilograms. Why 4 significant figures for 1.000? Those are 3 trailing zeros in a decimal point number, so they count. Trailing zeros count if there's a decimal point. All right, example. Do calculations and report the answer with the proper number of significant figures. So we may have to do addition and subtraction. We might have to do multiplication and division. All right. So here we have 4.87 milliliters plus 46.0 milliliters. Thankfully, when you do addition and subtraction, thankfully in this case, they're both in milliliters. You have to have them in the same units if you add or subtract. B, 3.4 times 0.023 grams. C, 19.333 meters minus 7.4 meters. D, 55 milligrams minus 4.671 milligrams plus 0.894 milligrams. So we'll be subtracting and adding 3 things in D, but that's okay. So A, the answer is 50.9 milliliters because the furthest to the right I go for both is the 10th place. B, 2 sig figs is it's 2 sig figs times 2 sig figs, so my answer, 0.078 grams, 2 sig figs. C, well, I can only go as far as the 10th place, 11.9 meters. D, looks like I'm doing addition and subtraction, and I can only go as far to the right as the ones place, limited by 55. 55 doesn't even have a point, so the answer is 51 milligrams. E is division, so it's 5 sig figs divided by 3 sig figs. My answer must be the 3 sig figs, 103. All right, converting quantities from one unit to another. This method is called the factor label method. I like to call it start with what you're given, put it over 1, and then follow the units from left to right. That'll make sense because I'll say it over and over. All right, the method is called the factor label method. I won't say that very often. I'll just usually use the term dimensional analysis. But in the next video, we're going to start off by giving you some conversion factors, and then we're going to start with what we're given, put it over 1, and then cancel units left to right until we get the units that we want to end up with.